Welcome back to my channel. First, I just want to quickly apologize. I am in the middle of getting ready to move in a few weeks, and so my apartment's a little bit of a mess. But I hope you'll bear with me. So today I wanted to make another astrophysics video, yay! And I wanted to talk about something that is pretty foundational to a lot of astrophysics, but that you may not have thought much about, and that is how we measure distances. So measuring distances here on Earth is pretty straightforward, right? Depending on the size of the object, you might grab a ruler or a tape measure, and I might be dating myself a little bit here, but when I was in high school, we used to measure our cross-country races using one of those rolling yardsticks. Do I even still have those? I don't know. Or when I was out running on my own, I would use my parents' minivan and I would just drive the route I wanted to run and use the odometer to figure out how far it was before I went and ran it. Nowadays, I have a GPS watch, which is a lot easier. So most of us are not really that used to, spending that much time thinking about how to measure things because it's pretty easy. But that's here on Earth. How do we measure things in space? There's not a tape measure long enough to reach the moon, and the moon is just the closest object to us. The nearest star, Proxima Centauri, is about 100 million times farther away than the moon is, and the opposite end of our galaxy is another 5 orders of magnitude, and that's still in the neighborhood, astronomically speaking. So, things are really far away. But how do we know just how far away those faraway things are? Our solution is called the distance ladder. That was me climbing the ladder. First, let's talk units. So this light year is pretty self-explanatory. It's the distance that light travels in a year. Here we take the speed of light to be the speed of light in a vacuum, and we take a year to be the Julian year, which is 365.25 days. This works out to about 5.9 trillion miles. Another common one you might hear in astronomy is Parsec. Not from Star Wars. I don't know what they were talking about. A parsec is about 3.26 light years. The official definition is that it's the distance at which one astronomical unit subtends an angle of 1 arcsecond, which raises a question, what's an astronomical unit? So that's basically just the average distance between the Earth and the Sun, which works out to about 93 million miles. So, got it? Good. Going back to the moon. We actually can measure the distance to the moon with great accuracy thanks to the Apollo astronauts who placed some reflectors up there, and we use those for laser ranging. So basically you measure the time it takes for a laser to go up, bounce off the reflector, and come back, and that tells you how far away it is, since we know how fast the laser travels. We can use a similar method using radar to bounce off objects in our solar system and measure the distances to them. So for asteroids, comets, and other planets, we can do that. But obviously, our ability to do such direct measurements like that is pretty limited, and radar and laser are relatively recent technologies. So what did we do before then, and what do we do for objects that are too far away to be directly measured like that? Well, geometry comes to the rescue. So for things that are close enough to us, which in this case will take to be about 1,000 parsecs away, we can measure them using some simple trigonometry. So as the Earth moves around the Sun, the stars that are closer to us appear to move relative to stars that are farther away, based on how far the Earth is moving. So that would be 2 AU in 6 months, right? From one side of the orbit to the other. And then the angle that those stars change based on that distance is based on how far away they are. So by measuring the angle that they move and knowing how far the Earth has moved, we can figure out how far away those stars are. This is called parallax. You can try it for yourself if you want by closing one eye and then the other and seeing how objects that are closer to you appear to shift relative to objects that are farther away. Camera 1, camera 2, camera 1, camera 2, camera 1, camera 2. There are actually several methods for doing parallax, such as using the sun's movement as the baseline, but they all follow the same concept. 1,000 parsecs isn't a bad start, but it's still a pretty tiny slice of the universe. So how do we measure things that are further away? Well, one major method that is used by astronomers is the measurement of standard candles. So a standard candle is basically something that we know the absolute magnitude of, which is how much light it is actually giving off. What we measure is what we call the apparent magnitude. So as light travels outward from its source, its intensity diminishes, and so the apparent magnitude that we receive is reduced based on the distance between the object and the receiver. So the standard candles, for example, might be something where there's a relationship between the period and the luminosity of a variable star. So we can measure the period here on Earth, use that to find the absolute magnitude, then measure the apparent magnitude, compare the two, and voila, we know how far away that standard candle is. Things that are near the standard candle, then we can, for example, a standard candle that's in another galaxy, we can measure how far away that galaxy is. We calibrate standard candles by basically identifying standard candles that are close enough to be measured their distance via parallax. However, there might not be any of the standard candles conveniently located with close enough for us to measure directly. So you have to correctly calibrate them and you have to correctly identify them. For example, there was an issue in the 1950s where it was discovered that one class of Cepheid variables that was being used as a standard candle actually had a different composition than the calibrated class of Cepheid variables. And the distance measurements were off by double. So we were measuring things that were actually twice as far away as we were measuring because we didn't understand and we didn't correctly identify these Cepheid variables at first. So like I said, Cepheid variables are one standard candle. Some other ones include type 1a supernovae and RR Lyrae variables, and there are other standard candles. Another method that uses a similar concept is called main sequence fitting. So the main sequence is a section of the Hertzsprung-Russell diagram that stars tend to follow along during the majority of their life. As we measure a group of stars and see where they fall on the main sequence diagram based on their apparent magnitude, and is displaced from where we would expect based on absolute magnitude, that gives us a relation between their absolute magnitude and their apparent magnitude, and again, that can give us the distance to those objects. So that method will be used more when you have a whole group of stars that you can measure, such as a globular cluster. But for all these methods, you're relying on the difference between the absolute and the apparent magnitudes to find the distance. You have to take into account other things that might reduce the apparent magnitude, such as interstellar extinction, which is basically the loss of light due to dust, gas, and other objects in between the source and the receiver. Now, as we go even farther away, we turn to Hubble's law. So Hubble's law tells us that the universe is expanding. And as the universe expands, light from more distant objects is speeding away from us. That relative velocity causes their light to be redshifted due to the Doppler effect. So Hubble's law gives us a relation between speed and distance, and measuring the redshift can tell us the speed, and therefore we can calculate the distance once we know the redshift. This is used for objects that are extremely distant. For example, the furthest quasar that we have measured using redshift had a redshift of 7.085, which corresponds to about 13.05 billion light years. That's pretty far. So the reason that we call this the distance ladder is that things that are further away rely on the closer methods that we've used. So we're basically laddering ourselves up from one method to another, and that also brings with it all the error from the previous level. So I've already discussed a little bit of the drawbacks referring to calibration, identification, standardness, and just plain bad luck whether or not we have things that are located within the calibration range. So distances within astronomy aren't always known to a very high degree of precision. If you're reading astronomical tests, you might see rather large margins of error, but we are continuing to improve and inch closer and closer to greater accuracy as we develop both our instruments that we use to measure the universe and our own understanding of what's actually going on in the universe. So this is just a very brief introduction to the distance ladder. It actually gets a lot more complicated pretty quickly, but I hope that you will maybe inspired to learn a little bit more. I think it is absolutely fascinating the way that we have discovered, just using our own ingenuity and wit, to probe the universe at these amazing distances, just sitting here on our little blue ball in our little corner of the Milky Way. I think it's great. So I hope that you want to find out more, and I hope you enjoyed this video, and I hope you'll be back for my next one. All right, thanks for watching. Bye. And radar and laser, laser.